relates a function to that function's derivative. So you have already seen differential equations, and that is whenever we have written derivatives with this notation dy dx. Okay, so that is a differential equation. It is saying that your derivative is equal to something here. So, so both of these would be considered differential equations. They are super duper simple differential equations because they're just in one variable there. So this is something that you have already seen. We have even solved differential equations somewhat, but they were super duper simple ones. Basically all we were doing was integrating, right? So like for example, if you were asked to solve this differential equation right here, you would multiply both sides by dx to get your dx over here. You got dy equals 3x plus 2 dx. You would integrate both sides. When you integrate dy, you just get y. And then over here, you would get 3/2 x squared plus 2x plus c. So we have done like the very most basic version of solving some differential equations. But we will, in this unit, be looking at some that are more complicated, some that involve x's and y's. So this first section here is going to focus on modeling situations. And these problems are basically going to be reading problems, mostly. There'll be a little tiny bit of math, but not much. And they're not the easiest reading problems in the world. So one phrase that you have to be familiar with is directly proportional. And we used to cover this a lot in Math 1, but they don't put these questions on there anymore, and I'm glad because the kids never really understood what it meant at that level, although it's very simple. Two quantities are going to be directly proportional if to get one, you can just multiply a number by the other. A really good example of something directly proportional is your paycheck is going to be directly proportional to the hours that you work if you're paid an hourly wage, right? So if I want to know what your paycheck is going to be, I would just take your hourly rate and multiply it by the hours that you work. That's an example of directly proportional. If you think of graphing it, it is just a line in which you have a y-intercept that's 0 and constant rate of change, right? So whenever we see something as directly proportional, we know that it means if we take one of the values and multiply it by some constant, which we typically use a k for, but you could use other letters, and then that will give us the other value that we're looking for there. So most of this is going to be reading to set up something as directly proportional. So if we look at this first example, it tells us the rate at which a quantity m of a certain radioactive substance decays is proportional to the amount of the substance present at a given time. Which of the following is a differential equation that could describe this relationship? So, again, it's mostly reading. So you can see right here we have this is proportional. They don't always say directly proportional. They might just say proportional. Either wording there means the same thing. So what this means is we've got some variable equal to a constant times another variable. So what we've got to figure out is what those variables are and what this will look like. You can see all of your answer choices are dmdt's right here. So that should narrow down one of them. But where that comes from, it says the rate at which the quantity of m decays, right? So rate that m is changing is what we have here. So rate of m, this part right here is dm dt. All right, because whenever we talk about rates, we're looking at that derivative. And it is proportional to the other part that we have right here is the amount of substance present. What is the amount of substance present? What's it going to be? It's going to be M. All right. And to get, like, it's easy, a little easier when it's multiple choice. Like you can see over here, obviously, it's either M or T. And although maybe it's not so clear that it's M, we know T is probably time here, so that is not going to be the answer. So this would rule out, since this is M, that rules out A and C because those have to deal with time. So the rate at which a quantity, so dm dt, is going to be directly proportional, we got some K, to the amount of substance, and M is the quantity of the substance. So that's the amount of substance times M. So if I look at this, it doesn't tell me what the K is. These are both of the same form. How am I going to know which one to choose here between B and D? Decreasing, so which one should I pick? B. All right. So since we're decreasing, we're going to have that negative value for our K. Okay. We eventually are going to get into like having specific situations and writing differential equations, solving to use this for a situation like radioactive decay. But right now, we're just thinking about setting up what it would look like to start with. So here's our next one. You can see these are terribly long problems. All right, so we got the population of a certain species of insect is given by a differentiable function p, where p of t is the number of insects in the population in millions at time t, where t is measured in days. When the environmental conditions are right, the population increases with respect to time at a rate that is directly proportional to the population. Starting August 15th, the conditions were favorable and the population began increasing. On August 20th, 5 days later, there was an estimated 10 million insects and the population was increasing at a rate of 2 million insects per day. Which of the following is a differential equation that models this situation? There's one of these that we can throw out from the very beginning. A is not a differential equation. It doesn't have anything to do with the rate. So A is going to be thrown out from the very beginning. Okay, because that deals with T, and this part right here told us that the population increases with respect to time at a rate, so that's your dp dt, that is directly proportional to population. So this is telling us that we've got dp dt is going to equal some k right here times p, not times our t. So we're going to throw out b as a possibility as well. And so for this one, we got to figure out the actual k value. Okay. So it tells us that on August 20th, 5 days later, there was an estimated 10 million insects, and the population was increasing at a rate of 2 million insects per day. It's going to be 1/5, because, like you've got, if you put in, the rate is 2, so we can plug in 2 right here. I got this k right here. That's my constant of proportionality. That's what I want to find. And then it tells me the population was 10 million there. So if I divide by that 10, I'll get 1/5 for my k, which makes sense here because if you're doing 1/5 times the population, that would give you the rate. 1/5 times 10 would give you 2. They give you extra information there. You don't actually have to know about that 5 days there for that particular problem. Okay, questions there? All right, let's look at another one. A scientist is studying a relationship of two quantities, S and T, in an experiment. The scientist finds that under certain conditions, the quantity of S increases, the quantity of T decreases. After taking measurements, the scientist determines that the rate of change of the quantity of S with respect to the quantity of T present is inversely proportional to the natural logarithm of the quantity of T. Which of the following is a differential equation that could describe this relationship? So I don't know why I didn't put the definition here, but inversely proportional, if X and Y are inversely proportional, that tells me that X is going to equal K over Y. So instead of K times Y, you would have K divided by Y right here. So you can see that you've got a K over something for a lot of these. Which one would you throw out? Knowing what I just told you right now, which one would you throw out? I would, just looking at this, I'd throw out B because the K is on the bottom. So it tells us that the scientist finds that under certain conditions, a quantity of S increases. The quantity of T decreases. Let's see. After change of the all right, so we're looking at rate of change of the quantity S, so that's our ds dt. With respect to the, oh wait, that should be a capital T, because it's ds with respect to the quantity of T, big T, is inversely proportional, K over the natural log of T. Natural log of T. So that would be C for this one. Why is it not A? Okay, this is not, S is not the rate. That would be the amount. So it's not going to be that one. And then this one is the natural log of S instead of the natural log of T right here. Okay, questions? All right, let's try another one. Jogger runs along a straight track. The jogger's position is given by the function p of t, where t is measured in minutes since the start of the run. During the first minute of the run, the jogger's acceleration is proportional to the square root of the time since the start of the run. Which of the following is a differential equation that describes the relationship where k is a positive constant? Okay, so all right, let's see here. So jogger's acceleration, P, what does P stand for? Position. So the jogger's acceleration, is that our first derivative or our second derivative? Second derivative. So jogger's acceleration, d squared P over dt squared, is proportional to the square root of the time since the start of the run. All right, so this proportional is where we put our k, square root of time since the start of the run. So that is going to give us C for this one. I pulled these questions from AP Classroom, and you're going to find that guessing C is going to be a good strategy on these problems. AP makes a lot of good problems that are used for like formative assessment. They're not like release test questions. They're ones AP's put out like to help you understand the section. And they are really good questions. They never mix up their answer choices any, and it's like they'll have two similar questions. They'll both have the same answer choice will be C. It's a little bit annoying. All right, try this next one on your own. All right, what'd you guys get? That is correct. So your differential equation dw dt, the rate that the weight is changing, is directly proportional to the weight. So K times W. So when the weight is 200, the rate is 5. 10 is extra. You don't use it. Divide by 200, you get 1/40. Questions on that? We'll probably work on the next one too. Alright. For that last one, alright. So, A, like on a lot of these, is not a differential equation, so it's out. If the pressure P applied to a gas is increased while the gas is held at a constant temperature, then the volume of the gas will decrease. The rate of change of the volume of gas with respect to the pressure is proportional to the reciprocal of the square of the pressure. So, rate of change of the volume of gas is dV with respect to pressure, dV dP. So, D is out because it's got dP dV. Is proportional to the reciprocal of the square of pressure. What's reciprocal mean we need to do? When you have the reciprocal of a fraction, flip it. Whenever you divide fractions, you multiply by the reciprocal. So the reciprocal means we need to do 1 over and then square of the pressure would be P squared. And then we got to figure out whether it's negative or positive. So we got K over P squared. Let's see. The pressure P applied to a gas is increased while the gas is held at a constant. The volume will decrease. So, the rate of change of gas. Let's see. But because the volume is decreasing, you would have a negative rate. So that K would need to be negative, or you would never get a negative for that. So, C would be your answer. So, everything was C except for number 1. There is no assignment that goes with this. There is going to be an assignment on 7.2, but we will